Hello! In today's lecture we are going to take a look at radiation of heat. All objects radiate, but our eyes are not sensitive to this kind of radiation, as most is in the infrared. So far we considered transport via diffusion or convection. These describe transport of mass, momentum and energy. However, for energy there is one more possibility that we have to take into account: radiation. Radiation is a form of energy transport, but now via electromagnetic fields. We are all familiar with this, as visible light is electromagnetic radiation. There is at least one important difference between, on the one hand, radiation and on the other hand diffusion and convection. Both diffusion and convection require a medium to transfer the energy. However, radiation doesn't. It works perfectly happy in vacuum. We know that too, as the sun heats up the Earth via radiation through empty space. Electromagnetic waves span many orders of magnitude in wavelength and thus in energy. The radiation is actually made up of photons, that are particles that carry the energy. The energy of a single photon is simply related to its frequency or wavelength. Energy is h times f is h times c over lambda. Thus long wave radiation carries little energy per photon, while short wave radiation is very energetic. In the slide you see the entire spectrum with the visible light as a very small band in it. Note the image of two people in the center at the bottom. Also we radiate with a wavelength of some 10 micron. For transport phenomena it is important to understand radiation as a way of transferring heat from or to an object. An object can lose energy by emitting photons. It gains energy by absorbing them. Both are always present, but in many cases their effect is negligible. However, there are also cases where it plays a crucial role. Hence, we will have to be able to incorporate it in our modeling. To do so, we first introduce the concept of a black body. That is an object that absorbs all incoming radiation. In 1900, the German scientist Max Planck derived an expression for the amount of energy that a black body emits per unit area and per second. It is distributed over all possible frequency, ranging from 0 to infinity. Moreover, this distribution is, if the object is in thermodynamic equilibrium, only a function of the temperature of the object. Planck found what is now known as Planck's law, that the energy radiated in the frequency range between f and f plus df is given by U sub f is 2h c squared over lambda to the fifth times 1 over the exponent of hf over k Boltzmann times the temperature minus 1. A pretty complicated expression that you can read on the slide. Luckily, we won't have to use this formula as such. In the figure, Planck's equation is shown for a few temperatures. It shows that the higher the temperature, the more energy is radiated. Moreover, the peak value shifts to smaller wavelengths, thus higher energies. As an example, the wavelength of the peak for a body temperature of 5000 Kelvin is given. It is 580 nanometers. That is orange light. The peak can be found by taking the derivative of the curve and setting that equal to 0. If you do that, you will find a simple relation between the temperature of the body and the wavelength of the peak. The product of the two is a known constant. This is known as Wien's displacement law. The small graph shows the peak wavelengths for different temperatures. From this graph we see that you and I, with our temperature of about 300 Kelvin, radiate at a wavelength of some 10 micrometer. This is in the infrared, and thus not visible for us. However, with an infrared camera we can easily detect this radiation. From Planck's law, we can compute the total energy flux radiated by a black body of given temperature. For that, we integrate over all wavelengths. The answer is given on the sheet. The radiation flux leaving the black body is a constant times the body's temperature to the power 4. This constant has its own name, the Stefan-Boltzmann constant, with a known universal value. The flux is thus written as sigma times T to the power 4. This is Stefan-Boltzmann's law for black body radiation, and this is our starting point for radiation in transport phenomena. However, black bodies do not really exist. A first step to real bodies are the grey bodies. These radiate according to the black body law, but with an emission coefficient in front of it. This coefficient, called E, has a value between 0 and 1. Note that this coefficient is a constant for the grey objects in question. It does not depend on the wavelength of the radiation. In the graph, we see that a grey body has the same curve as the black body, but with everywhere the same reduction factor. Real bodies have a more complex spectrum, as is indicated by the red line. It still resembles a bit the black body curve, but it's much more erratic. This is a consequence of the molecular structure of the substance of the object. One could say that the emission coefficient for real objects is wavelength dependent. A black body absorbs all radiation that falls onto it. Hence it doesn't reflect any back. No wonder it's called a black body. Grey values absorb a part of the incoming radiation and reflect the rest, or partly transmit it, but we leave that out of the discussion for now. They absorb a fraction A of the incoming radiation and thus reflect the fraction 1 minus A. The coefficient A is called the absorption coefficient. Kirchhoff showed that for an object in thermodynamic equilibrium, the emission and absorption coefficients are the same for all wavelengths. Let's do an example using black bodies. What is the temperature of the Earth? The Earth is in reasonable approximation a black body. Hence, it loses energy via radiation into space. If nothing else would happen, the Earth would constantly cool down. Luckily for us, the Sun shines on the Earth. Also, the Sun is in a reasonable approximation a black body. We know the temperature of the surface of the Sun, its size, as well as the distance to the Earth. Moreover, we do know the Earth radius. The Sun, treated as a black body, radiates according to the Stefan-Boltzmann law. Multiply that with the outer surface of the Sun and we get the total energy flow from the Sun into space. The Earth receives only a fraction of this radiation, namely the part proportional to the area of the Earth has of the total area of the sphere with radius Earth-Sun distance. Since we treat the Earth as a black body, all received radiation is absorbed. Of course, the Earth radiates itself, and thus we have another variation of the T to the 4th law. Since the Earth is in a steady state, we have in equals out, from which we can solve for the unknown Earth temperature. This simple model gives T Earth as 7 degrees Celsius, which is not bad at all. The actual average is 15 degrees Celsius. Okay, let's look a bit better to the fluxes of radiating bodies. If the body is grey, it will radiate a flux of E sigma T wall to the power 4. An incoming flux phi double in is partially absorbed, partially reflected. Thus the net flux into the body is minus what is radiated itself plus the absorbed part. It is minus E sigma T wall to the power 4 plus A times the incoming flux. Similarly, a flux E sigma T wall to the 4th plus 1 minus A times phi in is leaving the object. Do be careful here. We talk about the net flux into the body, not the flux into the body as such. So don't add these two net fluxes, as obviously the own radiation disappears as if it is not there. Finally, on this sheet is a table of emission and absorption coefficient for various materials. Do note that the emission coefficient is given for a temperature of 300 Kelvin of the radiating body, whereas the absorption coefficient is given for the absorption of sunlight. There are interesting differences. As expected, black paint absorbs almost all sunlight, whereas white paint reflects 90%. However, if we looked at their own radiation, they are both almost black. Dry snow also radiates like a black body and thus loses energy quickly, whereas it doesn't absorb much sunlight, thus it gains little energy. That is why it can stay snow for a long period. Alright, this was a quick introduction into energy transfer by radiation. Check out the glass plate examples to get a feeling for radiation. In the next lecture we will put this to practice. For now, good luck and take care.